Hello and welcome to this video. In this video we're going to go through the second half of fundamental particles, which is the leptons. So we said before that we can split all of the properties of the atom, so we can split the protons and neutrons into quarks, but the electrons, they stay as leptons. Okay, so we can't currently find anything smaller than an electron inside an electron. Okay, now I first want to go over what the difference between quarks and leptons are. Why is there the separation? Why can't we just call them all the same thing? How do we know one is a quark? How do we know that something else is a lepton? And so the difference is just that quarks feel what we call the strong force. Okay, now the strong force is something we're going to go over again when we look at fundamental forces, but it's there are, just like we have fundamental particles, we have four fundamental forces, which are the four things that govern all of the interactions that happen throughout the universe. The quarks are susceptible to the strong force. Okay, the difference is leptons don't feel the strong force. They don't feel strong force. Okay, and so we can't say they're the same thing because they are susceptible to different forces. So that's how we know there's a difference between them. Okay, now just like with quarks we had 6 different flavors, we also have 6 different types of leptons. Okay, so these types of leptons are what we've heard before. We know we have electrons. We have electrons, which we're familiar with. We also have what we call muons, and we also have the tau particle. Okay, some people will call it a tau or maybe a tauon. I call it tau. But these are different types of leptons. Now these are not very common. They only really happen when we force them to happen inside a particle accelerator. They will occur naturally, but very rarely, and only in like extreme conditions, like maybe in a star, they'll occur quite a bit. Okay, but essentially the difference between them is really mostly to do with their mass. Okay, so we'd say the mass of an electron we know is 9.11 times 10 to the minus 31. Muons will be bigger than that, and then tau will be even bigger than that. So the mass just increases as we come down the group. So as we go down here, the mass increases. Okay. And so there isn't a table for this stuff in the in your formula sheet, but you will have to know this. So the charge of each of these things is negative the charge of an electron. Okay, so we should know by now the charge of the electron, I'll write it up here again just in case, is 1.6 times 10 to the minus 19 coulombs. So this is in coulombs. So the charge of an electron is just negative this value, and all of the charges of these things are the exact same. Okay, so they have exactly the same charge. We said their masses generally increases. Now you don't need to know the specific values other than the electrons, so I'm not going to write down what the mass of muons and tauons are in kilograms, but you have to know generally their mass increases, but they also have something called the lepton number. Okay, so just like if you remember back to the quarks video, we had something called the baryon number. All quarks have the same baryon number, all leptons have the same lepton number, and all leptons will have a lepton number of 1. Okay. Now, I did say to start with there are 6 types of leptons. Okay. Now the reason I've split this into 3, and I'm going to do another table, or I'm going to draw a little line between these and do another section of this table, is because the other 3 are very weird and they don't have mass or charge. Okay, so these are called neutrinos. Okay, so I'm gonna put it here so that this is this side underneath this dashed line of neutrinos, and we have a neutrino that's specific to each type of lepton. So we have an electron neutrino, we'll have a muon neutrino, and we will have a tau neutrino. Okay, now the charges, like I say, they're neutral. They have no mass and no charge, which basically makes them almost impossible to detect, because all the ways we've detected things like electrons and protons is we put them in a charged field and they bend because they are charged, and so we can see that they go in different directions because they have different charges. In the case of neutrinos, we have to get very sensitive equipment in order to detect neutrinos even existing in the first place. But they will still have a lepton number of 1. I'm also going to put a star next to this no mass. For your A-level spec, you will have to treat them as if they have 0 mass. We found recently, so like 2015 I think it was, that they do have a very small mass. It's about 1 billionth times smaller than the mass of an electron, but it does, or certain ones that we have found do have mass, so we assume they all have mass. So we're going to treat it as if there's no mass, but it does have a very, very tiny amount of mass there. I just don't want to provide you with any information that then you go online and see that there's actually something that's different. They do have mass, but when the spec that we have was written, we didn't know that, so we're just going to treat with the spec that we have no mass. Okay? And they definitely have 0 charge, but their lepton number is 1. Now, we also have the antiparticles to all of these things, but one thing that I'm going to make sure that we know is the symbols. Okay, so I'm gonna get rid of this list here, and we need to know the symbols of each of these things, because they're never gonna, they're most of the time not gonna tell you it's a muon. They might just give you the symbol of it. So electrons, we know, are just E with a negative charge. A muon has this Greek symbol mu, so it's like a U with like a fancy tail at the start with a minus, and then tau is like a curly T with a minus there. Now all the neutrinos all have the same symbol, so that all the neutrinos are the symbol nu. So this is the symbol nu. If you want to look it up and find a better drawing of it, it's basically a curly V. And because this has a specific type, this is an electron neutrino, it becomes mu E, it becomes mu, and this becomes nu tau. Okay, so these are the symbols. So they can ask you sometimes to just be able to recognize the symbols. Granted, they're probably not going to ask for tau or tau neutrino. In the same way, they're not going to ask about top, bottom, or charm quarks, just because they get a lot more massive, and then they get a lot more complicated to deal with when they're at higher energies. And so this is what we need to know about leptons. Okay, we need to know that these things exist, and we basically only need to focus on electrons, muons, electron neutrino, and muon neutrino. Now, obviously, as always, we can have antiparticles to this. If we have an antiparticle, the antiparticles, the only thing that's going to change is all of the lepton numbers become -1. If we wanted to say the name of all of these antiparticles, we literally just put anti in front of it. So it would be an anti-muon, anti-tau, anti-electron neutrino, anti-muon neutrino, anti-tau neutrino. Notice I've missed out the electron, because the electron, the antiparticle of an electron is what we call a positron. Okay, I think I mentioned this in the quark video as well. The reason it's called a positron is because we found out about it before we knew that antiparticles were a thing. So we thought we discovered a whole new new particle until we realized that all of these things are just antiparticles of each other. So it's literally just the opposite of what it should be. And the other thing that's going to change is just that their charges are going to become positive here. Okay, so charge becomes plus E. Obviously, the charges of something that has a charge of 0 can't become minus 0 because minus 0 isn't a thing. So the charge of this doesn't change, the charge of these neutrinos, but the lepton numbers will. And the symbols of them, all of these will just become, so the antiparticle symbol, I'm just going to write alongside them all. So the antiparticle of the electron is the positron, the antiparticle of mu minus is an anti-muon, and anti-tau. This becomes the electron neutrino with a bar on the top. Remember this bar, like we had for the down, up, and strange quarks, is just a bar, and then tau with just a bar on top. Okay, so these are all the particles on this side and all the antiparticles on the second hand side. Okay, so this is everything we have to know about leptons. They don't form anything like quarks form things, so leptons are a little bit easier. All of these symbols, along with whether their lepton number is plus 1 or minus 1, is in a table in your formula sheet on the second page, just under the quarks table as well. So if you're ever stuck on whether it's a lepton or an anti-lepton, you can always just check back to your formula sheet, so you don't actually have to memorize any of these things either. So hopefully this all makes sense. Thank you for watching.